Hello there and welcome back. Today we're going to take a look at finding volume between two curves, very similar to something we did last year in single variable calculus. And we're also going to be taking a look at how we find the average value of a surface, of a volume right here. So let's review a little bit from calculus last year. So last year we learned how to find the area between two curves. You may recall that if the rectangle was vertical, we used the top to bottom method to find the area of that rectangle. So let's take a look at an example. So if I have two functions here, one f of x and one g of x, it's a sad function, and we're looking at the area between them. So what we would always say we can do is we can draw a vertical rectangle between them, like so. And if I blow up that vertical rectangle, we'll call it dx, I can get the height of this rectangle by taking the top function f of x minus the bottom function g of x. And therefore, my area would be the area of the rectangle, the length, which is f minus g, times the base of the rectangle, dx. Now, to get the domains, you might remember we had to look at the intersection. Where does g equal f? And in this case, we got some a value and some b value when we solved that. And that is how we would get the area between two curves. Very easy function. So today we're going to take a look at the exact same concept, but now we're looking at volume. So when we are evaluating the volume between two surfaces, the technique is the same. To find the volume of the solid region bounded, so let's go ahead and find the volume of the solid region bounded above by this paraboloid, 1 minus x squared minus y squared, and below by the plane z equals 1 minus y. So we kind of see that image right over here. We have this paraboloid and we have a plane slicing it. What we want to do is find the volume of the area in between. So we want to find the volume between the two surfaces. So that's what we're looking for here. The volume, we want the volume between the two surfaces. So the first thing we're going to look for is the base region. Remember, we talked about this in the other past few videos. To measure volume, we are going to take the area of the base. Remember to get volume. We're going to take the area of our base and multiply it by our height. Well, so my base is a projection. So that's really kind of the trick to today. So to get the base today, let me go ahead and write that down here instead. So to get the base, we are going to look at a projection. So if we imagine a light shining straight down from above, it's going to come down and strike perpendicular to every point on these surfaces. But right over here, I'm looking at this little part right here, how light strikes down here. And if you notice down the bottom here, we have our base. And we have to find the equation of that base. Well, how do we do that? Well, it is going to be very similar to how we found the domain. We're really looking for where on the xy plane is the intersection of our plane here that they give us and our paraboloid. So we are going to let, that went crazy. So we are going to let z equal 1. Now you might recall if we let z equal 1, this becomes a trace. This is going to become a trace on the xy plane. So what we're looking for is the trace on the xy plane of the intersection between our plane and our paraboloid. So a real quick way to do, not 1, but 0, sorry. Not 1, but, come on. We want that to be 0 there. Sorry about that, the xy plane was equal 0. So the best way to do this, so these are both, sorry about that, my keep going crazy. So if we let both z's equal 0, well then we know that these two functions could also be equal to each other, so that the paraboloid could equal the plane. So we're going to write that out. So we can say 1 minus x squared minus y squared equals 1 minus y. Solving this, we would get x squared plus y squared plus y equal to 0. And you might recall what shape this is. This is a circle on the xy plane. Now, if we complete the square, we can actually find out the center, location, the radius, and everything of the circle, which is something we will probably need to have. So let's go ahead and do that. If we complete the square, we get x squared plus, this becomes, what's that, half of y, half of 1 is 1/2, square we get 1/4, so we get, what's that, y minus 1/2 squared equal to, remember this was at 1/4, so to fix it we're going to add 1/4 to the other side, and there we have our circle equation. We know our center is going to be 0, 1/2, and the radius is also 1/2 right there. So let's look at that. So that's going to give us the trace. So we're going to project this circle up to the intersection, and that projection is going to help us get the volume. That's like our little funnel. Okay, so everything between that circle and the xy plane, we're looking for the difference now between the plane and the parabola, the difference in their volumes. So very similar to what we did last year. So let's continue and look at the base. If we look at our circle now, if I were to draw this on the xy plane, my center we just said is at 0, 1/2, and has a radius of 1/2. So it looks like this. So that's negative 1/2 on the x, positive 1/2 on the x right there, and on the y it goes from 0 to 1 on the y. So now we just have to make a choice. Do we want to go horizontal or vertical for our equation? So in this case right here, I'll be honest with you, if I just look right here, it's a lot easier to solve for x. So I am going to use a horizontal rectangle right there. Whoops, there we go. I'm going to use a horizontal rectangle. So remember, that's going to give me my change in x. But to get my change in x, I got to get the equations of this circle. So we know that x squared plus y squared minus y equals 0. So solving for x, we would get plus or minus the square root of y minus y squared. And that's going to give me my change in x's. Negative root y minus y squared, positive root y minus y squared. Now, my changes in y's, they're going to go from 0 to 1. Alright, so now that we got all of this, I know it's a lot, we are now ready to set up our... So, remember, we got our domain by looking at this circle right here and looking at the graph. So now we're going to go ahead and set up our volume equation. Now, we might remember from calculus, to get the volume here, we would take the volume of the outside function minus the volume of the inside function. So if we're measuring up right now, on the very top is our paraboloid. If we're looking at the intersection of our plane and our paraboloid, the paraboloid is going to be on top. So we want to find the volume of the paraboloid and subtract the volume of the plane. Pretty easy to set up. So my volume will equal, it's going to be a double integral because remember we're looking at the projection of our plane and we're going to project it up there. So this is going to be our iterated integral right here. Okay, well how do we get the paraboloid? Well, the paraboloid, remember, was this 1 minus x squared minus y squared minus the volume of my plane, which was this 1 minus y dy dx, and remember my change in, we switched around, excuse me. I'm so used to going vertical, but this should be dx dy because we went horizontal. So my change in x's we said was negative square root of 1 minus y squared to positive square root of y minus y squared, and then the y's will go from 0 to 1. And there is our equation. And we would just type that in a calculator. If you really like yourself, you can solve that by hand. Alright, go into video number 2 and we'll take a look at a couple more examples.